Now you have enough knowledge to discuss one of the most important part of this course, how to use any theoretical distribution. The things that we are going to discuss in this relatively short video are very important for understanding the rest of the course. So please pay additional attention to this video. So the idea is following. Remember, this is how we describe the normal distribution, right? We say the value x, it's our observation. We observe the value x as it is because of two things. First of all, because this value came from population where we have some fixed parameters, right? So if you use normal distribution, these parameters are mu and sigma. And second, because we also have a random effect. So we have this randomness, and this random factor, actually, it's the one that follows this distribution. So in this case, normal distribution, right? So x is a combination of something systematic, something fixed, and also the randomness. Okay. Now, it means that we have two ways of using distribution. So you can think about distribution, it's the way to handle this randomness. What are the two ways? Well, either you can assess extremeness of your value for given parameters. So it means that in this case, we kind of assume that parameters are known, and then we can assess how extreme your value is for these given parameters. Or you can compute interval. You can compute interval of your values for different probabilities. So this assessing extremeness or computing interval are two most important ways to use any theoretical distribution. What's the difference? The difference is very simple. It's the way you estimate z-score. So if you estimate z-score based on your values, you will compute extremeness. You can assess the extremeness, how extreme your value is for a particular set of parameters, right? For particular population, for particular sample. But if you assess z-score based on the probability, so it means that you can assess, you use theoretical distribution to assess z-score, then it gives you a possibility to compute intervals. Let me show you some practical examples in order to make it more clear. So let's start with extremeness, right? You can see in extremeness, you take a value, then you compute z-score based on this value, and then you compute a probability based on the z-score. So this is the direction of the computations, right? So what it means? It means that x is already observed, given, observe, measure it, whatever. Then z-score is computed based on x and parameters, and of course you either know parameters of population or you can estimate these parameters by computing sample statistics. For example, if we talk about normal distribution, you can compute average of x, standard deviation of x, and use them as estimates for population parameters. And then you compute the probability based on the z-score and the particular theoretical distribution. So this is the procedure. Now let me show you an example. The example I'm going to use, it's similar to one of the examples I used before. Let's say that we have a company and we know parameters of this company. These are parameters of salaries. So we know that salaries of the company is distributed normally. Average salary is 30,000 krona and standard deviation is 5,000. Now John says, my salary is 50,000. I work in this company ABC and my salary is 50,000. How likely is it possible? Can we say indeed that John doesn't lie and John indeed works in ABC, right? So it means that we need to assess how extreme this value is to be taken from this population. So we assess extremeness of the values. So how we do that? Well, you remember this is the procedure, 1, 2, 3, right? First we have the value, it's 50,000, it's already given. Now we need to compute z-score based on this value. Well, you remember z-score is, if you know the population parameters, either real population parameters or estimated, then the z-score can be computed by simply you subtract mu from x and then you divide to sigma. Z-score shows you how many standard deviations you're x away from mu. And that's exactly my computations. You already can see that it's very extreme. Why? Because we know that in normal distribution, 99.7% of the values lie within 3 sigma, right? So and you have 4 sigma. So it's already almost unlikely, right? Now, if you compute, how to compute extremeness? Well, you can compute a probability to get this z-score. Not exactly z-score, it's impossible, but you can compute a probability to get z-score smaller than this one or larger than this one. For example, if I compute probability to get this z-score smaller than this one, this is the probability. So what's the meaning of this? It means that 99.99683% of all employees in the company have salary smaller than John. Or you can compute the other tail probability, the right tail probability. So this is the chance to get a person in this company who have salary larger than John's salary. And you can see it's almost zero. It's very unlikely that there is anyone in this company who actually have salary larger than John's. So either John lies, or he is, for example, he's a top manager in the company and has the highest salary, which is way above the other ones, right? So that's the extremeness. So it's still possible. It's still possible to have this value from this population, but it's very, very unlikely because the probability is very small. So that's the first way to use any theoretical distribution. It's not only normal distribution, but any theoretical distribution can be used like this. You get a value, you compute a score based on the value, and then you compute a probability based on the theoretical distribution that describes distribution behavior of this particular score. Okay. Now let's talk about how to compute intervals. It's also based on Z, but now Z is computed based on theoretical distribution, not based on the value. So let me show you again the procedure. First, you need to define a probability for your interval. For example, if we talk about intervals, we usually talk about intervals of most common values, which are located in the middle. And then you can think about 50% interval, 90% interval, 95% interval. That gives you an idea of which probabilities to use for computation. Then you compute z-score for the given probability. In this case, your z-score is computed not based on sample. It's computed not based on value. It's computed based on theoretical distribution, right? And then you compute a values of your boundaries, of your interval boundaries, based on the z-scores and the parameters. So again, let me show you an example. We use the same idea, the same story, salaries in company ABC, average and standard deviation. Now, what is the salary of 95% of employees? We are talking about most common values, most expected values, so it means that they are located in the middle, right? So you remember that if you think about any distribution, not only normal distribution, but any distribution, if you need to find interval of 95% of most common values, it means that you need to find two values, which will be boundaries of your interval. So area under PDF curve between these two values is 0.95, right? But if area is 0.95, it means that for this value, the area on the left is 0.025, right? So it's 2.5%. And for this value, area on the left, it will be 95 plus this one, right? So it will be 0.975. So you know these two probabilities. So this is a probability to get a value in between. This is a probability to get a value smaller than the left boundary. This is the probability to get a value smaller than the right boundary. Now we have probabilities. So this is done. Now we compute z-scores for these probabilities. The z-score for the left boundary we compute using theoretical distribution, ICDF function for normal distribution. We simply provide this probability, and then we get a z-score for the right boundary. Then we do the same for the left it's z-score for the left boundary, and this is for the right boundary, right? So again, we compute it based on the probability. Of course, a normal distribution is symmetric, so actually I can skip these two steps and just make a one, because I know that z-score for the left boundary will be negative of z-score for the right boundary, right? But in this case, I want to make this procedure versatile, so it will work for any distribution, also non-symmetric distribution. That's why I do it like this. And now we know that, okay, we know z-scores, so we know z-scores, we know parameter. Now we can compute x. So x for the left boundary will be mu plus z-score for the left boundary times sigma. So that's the value for the left boundary of my interval. And this is, again, mu plus z-score times sigma. So that's the value for the right boundary of my interval. So now I know that 95% of the values 95% of the employees have salary between these two. And then 5% are beyond. 2.5 have salary smaller than this one. And 2.5% have salary larger than this one. Okay. And once again, this is the way we are going to use any distribution. either we assess extremeness of the value. In this case, for given value, we compute z-score based on the value. And for given z-score, we use CDF function, right, to get a probability to get a value as we have or more extreme. And then more extreme, it depends on what you define as extremeness, larger or smaller usually, right? So this is the way. And the second way is to compute intervals of most common values. And in this case, you do the other way. You can see that if you look at this procedure, you can see that here we go from x to p, and here we go from p to x, right? So it's kind of other way. So first you define a probability, then you compute z-score based on the probability. So you use ICDF function here, ICDF function, and then you compute x based on the score, on the standard score. And that gives you an interval because you have to compute two values, two z-scores and two values, one for the left boundary, one for the right boundary, and that gives you the interval. Of course, you can also compute quantiles, meaning not intervals, but just single values. But anyways, you use this way, right? So either z-score based on the values and then probability based on the z-score, or z-score based on the probabilities and then the value based on the z-score. Okay. We will use this procedure quite a lot in the block number 2. So please, if necessary, watch this video again. Try to compute all these exercises that I used yourself. It's very important that you understand this procedure. So in the last video, I'll show you how to do all these computations, plots, and normality test, and many other things in R.